As usual, when looking at algebraic expressions, I like to start with the graph. Recall that slope equals rise over run. In this case, the rise is a change in velocity, and the run is a change in time. Change in velocity over change in time, that's acceleration. So in this case, velocity versus time graph, the slope is the acceleration, and here's our formula. Let's check the units. Acceleration is meters per second per second. Velocity is meters per second, and time is seconds. So the units check out. And a quick reminder on how to rearrange this equation. So if we want change in velocity isolated, we can multiply both sides by delta t, giving us a times delta t equals delta v. And then if we want the time interval isolated, we can then just divide both sides again by acceleration. And there you have it. Okay, first example, read the question. In this case, we're not interested in just the change in velocity, we're interested in finding the instantaneous velocity at a given point in time. So we need the equation of this line. If you think of the general form of a linear equation, it looks like this, where m is the slope and b is the y-intercept. In our case, the y-axis is velocity, and the x-axis is time. So we see those two variables down here. That makes this the slope, and this the y-intercept. So right off the bat, we can narrow it down to one of these two equations, because they both have a y-intercept of 7, like our line, and then we just need to figure out the slope. In most of these cases, it should be relatively easy to tell which one is which. The slopes are far enough apart, 3.2 and 0.3. In this case, we're going up about 3 and over 10, so 3 over 10.3. It's gotta be this one. Alright, here we go. Example 2, read the question first. Okay, so let's see what information they gave us. They gave us the acceleration of 3.2 meters per second squared, and they gave us a time interval of 12 seconds. We want to know the change in the car's velocity. So here is the variable we need to isolate. So let's work on doing that first. We can multiply both sides by the time interval. And there we go. Change in velocity is going to be the acceleration times the time interval. I leave it to you to plug those in and find the change in velocity. Don't forget to make sure the units work out. Okay, next example, make sure you read the question carefully. In this one, we're asked to find the boat's final velocity. So we can look at the equation. Final velocity is equal to the initial velocity plus any change in velocity. That should make sense. Let's say the boat starts with a velocity of 6.2, and then the change in velocity was 1. What would the final velocity be? Sure enough, 7.2 makes sense. We're just adding those two together. In this case, they didn't give us the final velocity, though, so we can't use that. But if you recall from the first slide, and you should have this written down, the change in velocity is given by the acceleration times time. So now we have the initial velocity, the acceleration, and the time interval. I leave it to you to find the final velocity. Okay, last example, read the question. And in this one, they're asking us how far the car is going to travel in a certain time period. So we're going to need our displacement equation. I just want to remind you where that equation came from. If we look at a velocity time graph for changing motion, it might look like this. And if we want the displacement from this graph, we need the area underneath the line. And since the area of a triangle is 1/2 base times height, our displacement can be found by doing 1/2 the change in velocity, it's over here, times the change in time. There we go. Looking back to our original problem, they gave us the change in velocity, 0 to 33 meters per second. It's going to be a change of 33 meters per second, and the time interval was 3.8 seconds. I'll leave it to you to plug those in and find the displacement.